Yeah, so I will wait for a little bit more time. Yeah. So, am I audible first? Can anyone confirm?
Yes, you're audible.
Okay, and is the screen visible?
Yeah.
Sorry? Am I sharing the screen now? I think so.
Yes, your screen
Yeah.
is visible.
Okay, great. Yeah, so I will just wait for a little bit more time so that everybody can join. And then we shall start. Yeah, so before going into the calculus part of like what we'll be dealing today mainly, before that, let me just quickly go through few of the important things and comments on the mock test 2 and the mock test 3. Maybe not mock test 3 debate. I think it will be better to discuss that after the copies have been graded. Okay, so yes, just let me. Yeah. So I think the objective part is quite clear to all of you, right? Is it? In mock test 2, is there anything to discuss about the objective part? So the answer to the first question will be 2700, and that's quite easy. Like 77 is factored into 7 times 11, and so the first part can be 7 or can be 11, and when it's 7, then the second part of the product is 11, and so on. So you can just calculate the thing. And of course, one more thing, as many of you are solving most of the questions, at least in the case of mock quiz 2. So it's very much beneficial to discuss among yourselves. So suppose you were stuck at one problem after the exam, you can of course go to some, you can just discuss in the group or wherever else. So yeah, and all the problems in the objective part is basically easy in mock quiz 2. So the question number 8, where the question says that there is always a rational number in the interval closed AB, where A and B are reals. So here, the thing is to notice that A and B are not given to be distinct real numbers. So I think it's very well known that if A and B are distinct, then for any interval A and close A close B, there must be a rational, and also there must be a rational in the interval. But yeah, so the point here to note is just making the points that the singleton is also a closed interval in R. This is something we often forget. And then, yeah, so there is a continuous function which is differentiable exactly on one point. This is something interesting. And I think most of you did this correct. The example is also very interesting. So this is also something you should know, that there is a function which is continuous everywhere. There is a function. There is a function which is continuous everywhere and still differentiable. This is called the Weierstrass function. You can just look up and see how the function is. It's a very pretty interesting example. And essentially from this you can construct functions which are continuous but differentiable on exactly one point, or at exactly some n number of points. You can construct it there. Let's try to do like that. And yeah, so there's nothing much else to discuss about the objective part. In the subjective also, I think, yeah, so the questions were pretty easy. The first one is just modulo check and number theory. The second one, you need to take, like, you need to prove something on induction, and by that you can prove that the such function doesn't exist. Some inequality you need to prove by induction. I think that question was also included in the model test paper or the model paper you got. And the third one is you have to take the minimum and the maximum and then sort of find a path between them and do some things. So that also many people have solved. So you can just, if you haven't solved it yet, you can just ask them and get the solution. The fourth one is also, again, some substitutions, and then the limit will go to x to x plus pi or something like that, and x going to infinity, and then you can apply something and get the result. The fifth one is just counting in two ways, two different ways to get the identity. The sixth one, you can apply CS or whatever you want to get the inequality. It's just that you can take px times p of 1 by x should be greater than or equal to p1 or p1 square or something like that. That's also very easy. And then the seventh one, yeah, the seventh one is just checking the inequalities, putting values. So if there is any like specific doubt about any question, you can ask now in mock quiz 2. And the eighth is also very simple. You can just directly apply Kittu's lemma. And yeah, so few things while applying Kittu's lemma. Suppose you were applying Kittu's lemma in a problem in ISI inference or CMI. So it's best to state the lemma first. And of course, if you have time, it's also good to prove it using CS. So I think, yeah, so many of you did that. It's always playing on the safe side. Like, yeah. So that's it about mock test 2. I don't think there is anything else to discuss. And just a clarification about mock test 3, question number 1 in the subjective. That is something. Actually, the statement of the question is a little bit ambiguous. So just let me check if all have joined. Yeah, I see. So yeah. The issue here is we have a polynomial fx such that mod of fx is also a polynomial, right? And then it's told to find solution of fx plus 27x squared equal to 0. So now, yeah, so there are many logical questions here that solution. So what kind of solution we are looking? We can look at solutions for x. We can search for solutions for fx, which is a real polynomial. So it's not mentioned in the question, and that's a fault of it. But of course, so this is also something to be prepared of. Like, you might have to face some problem in ISI entrance, which is somewhat ambiguous in its terms. So in that case, you need to go with your intuition and see what are the important parts of the problem and try to write it down. Because maybe in the future they are giving marks like grace marks on that question or whatever, but it's always best to try the thing. Like, of course, you will understand something and maybe they are meaning something else, but still it's good to write the thing down on paper. So anyway, so I think here they are searching for solutions of fx because solutions for x is not very clear here. So I think it is meant to be like this, that fx plus 27x squared for equal to 0 for all x. If fx is a polynomial satisfying this, and also the above condition that fx and mod fx both are polynomials, then what can you say about the polynomial fx? Like, can you give me a particular solution of fx or a class of solutions of fx or something like that? So then the problem is, I don't think it's very difficult. First, looking at if fx is also a polynomial and mod fx is also a polynomial, we can say that f doesn't change signs. So either f is greater than or equal to 0 for all x, or f is less than or equal to 0 for all x. So now, keeping that in mind, if we look at fx equal to like fx plus 27x squared is equal to 0 for all x, we get fx equal to minus 27x squared for all x. But then also it doesn't make sense, rather. So I think there should be a square or something like that. Like, I think they're trying to use this f is always greater than or equal to 0 or f is always equal to 0 thing in some sense in solving the equation. So I don't really know. Like, it's a little bit ambiguous in its part, in the last part of it. But yeah, so the thing is that at least when somebody will grade your papers, they will look at the point that have you reached this place. And that is all you can say about it, really. So given the information that fx and mod fx are both polynomials, this is the only thing you can say about polynomial. Like, you can't extract any more information to begin with. So that's it. And I think the rest of the questions were fine, like no clear ambiguity or something. So yeah, so we can discuss that later. So yeah, so let's move on to the main part. That is, today we are going to discuss some standard notions of grid analysis and also solve few problems. So before starting, what we should do is go through a few rapid questions, rapid problems. So tell me something. What do you mean a function? What do you mean by a function to be non-increasing? So when I say that f is non-increasing, what does it mean? On, let's say, on an interval, on. So what does that mean? Anybody? You can unmute yourself and answer.
xn plus 1 is less than or equal to xn for all natural numbers. Like for
what is xn?
I mean, for the function, the function is either constant or decreasing.
Okay, and what do you mean by a function to be decreasing? Okay, so is it the function is
So
constant?
if there are 2 points x and y in the interval ab, so that x is less than y, then fy is less than or equal to f of x.
Okay, so fx is greater than fy. That's what you're saying, right? So okay, so is it correct?
There should be an equality sign also. So it's greater than or equal.
Equalities. And what about this separate case? So do we really need this separate case that it is constant?
Oh no, I actually changed my answer. So my answer is just the last one.
Yeah, absolutely. So that's what we mean by this. So another thing is that when we call a function to be decreasing, what do we mean by it? We mean it's strictly decreasing or it's decreasing in this weaker form. That is something it depends on the book, like depends on author and depends on context. So I think when if something like this is asked in the exam of ISI or CMI, they will specifically mention that what do they mean by saying that a function is strictly decreasing or anything like that. Okay, so that's something which is clear to us now. And for a function is f is non-decreasing if fx is greater than equal to fy if x is greater than y. That's the thing. Now tell me this: if suppose f is a function from closed AB to R, and f dash 0 is greater than 0. So can we say that f is increasing at 0? So now the first question is, what do we mean by saying that f is increasing at 0? So please unmute yourself and answer. So I want it to be as like the class must be very interactive. What do we mean by a function to be increasing at a point? What do you think?
Increasing in a small neighborhood around that point.
Yeah, and what does that mean? Like explicitly, mathematically.
So there exists some delta greater than 0, so that f is increasing in the delta neighborhood of that point.
F is increasing in the delta neighborhood of the point. That is minus delta vector, right?
Yep.
Yeah. So by that you mean that for all x not equal to y in minus delta to delta, if x is less than y, then fx is less than equal to fy. But this is not exactly true. So that is the point I'm using. So what we mean by increasing at a point is necessarily this, okay, that there exists, as you said, delta neighborhood around 0, such that for all x in delta, if x is greater than 0, then fx is greater than f0, and for all y in delta, if y is less than 0, then fy is less than f. This is what we really mean by saying that a function is increasing at a point, let's say here 0. So can you spot the difference between the two definitions? And the sad part is that they're not equivalent. So what I'm trying to say is that there can be a function which has a positive derivative at a point, and still there might not be any interval around that point where the function is increasing.
Yes.
Yeah, so that is the thing, and this is something we confuse generally. So increasing
X plus
on a
x plus sine 1 by x example of such a function.
yeah, so can you just please say your name while speaking so I can just understand with whom I'm communicating?
I'm Shivanti.
Okay, great. So yeah. I think that is an example of such function. Yeah. So that is really an issue, when we're talking about definitions, results, and whatsoever big theorems of calculus or real analysis, we miss all those small details associated with it. And you might not see how it affects your problem solving, but let me assure you it does. So what we'll do today is look into some of those important and often misunderstood concepts and solve some problems. Yeah. So let us start with solving a problem, right?
Can you explain that increasing at a point thing again? So, I mean,
Sure. Yeah.
so if the derivative of f at that point is greater than 0, then it's kind of easy to understand that it is increasing. But what if it is not differentiable at that point? How do we identify?
Easy to understand is increasing. So again, increasing in the sense I say, like increasing in the sense of a point-wise increasing thing, not an interval increasing. So a derivative cannot conclude anything about being increasing or non-increasing in a particular interval. That is something to be understood. A derivative can only say about being increasing on a particular point where the thing is differentiable. Okay. And yeah, so if the function is not differentiable, then you can't say anything about it.
If a function is differentiable in a closed interval and the derivative in that interval is greater than 0, can't we say that the function is increasing in that
Very good.
interval?
Yeah. So that is where I was going. So suppose if the f dash f is differentiable on closed AB, and f dash x is greater than 0 for all x in AB, then can we say?
I think in that case, f will be increasing in this interval.
Exactly. Right? Right? Can you prove it?
I think from the form of the definition of a derivative, we can do that. I guess I don't remember the proof actually. And we can write the derivative at some point, like at point C, it is limit x tends to c of x minus fc by x minus c. In that way, we can prove this.
Okay. So I don't see how you can prove it, but yeah, you can. I guess you can. Yeah. By the definition of derivative. But yeah, so I think what you really need here is one fundamental thing. Again, a asterisk thing here, that f dash satisfies intermediate value. So what is that? Anybody? So and please, like, I want to hear from all the different people in the class, and just don't hesitate. Okay, just feel free to ask, and feel free to stop me wherever you can. Anyone? What do you mean by an intermediate value property of function or intermediate value theorem? You of course know intermediate value theorem. So what is it?
Sir, if k is any value between f dash a and f dash b, then there exists a c belonging to open interval AB such that f dash of c is equal to k. This is the IVT for it.
Exactly. So yeah. So what I'm trying to do is actually know that from what kind of background you guys are now, so that I can go on to that level of problems and stuff. So because it's such a short course, it's not really easy to go through all the small details of the subject. It's such a big subject, right? So yeah, so I am assuming that all these small theorems and things you all are comfortable with, right? So yeah, so IVP is exactly that. It's the intermediate value property of f dash, which says that if I am saying in a little bit less general way, if f dash x is less than 0 at some point, and f dash x2 is greater than 0 at some point, and x1 is less than x2, then there exists a x in between x1 and x2 where f dash x is 0. So exactly that. And now this is true because if not, then there exists 3 points x1, x2, x3 without loss of generality, such that from x1 to x2 is increasing and from x2 to x3 is decreasing. And then you need to apply MBT to say that here there exists a point where the f dash is greater than 0, and here there exists a point where the f dash is less than 0. And you can do stuff like this. So if there is some point where f dash is equal to 0, and stuff. So that's something you can do. And I don't think you really need IVT here. So you can just say that there is some point where f dash is less than 0. But yeah, so you can also say that if there is a function which is not having derivative 0 at any point in the interval, then at that interval the function is always strictly normal. But the converse is again not true. So let me go to this part. I think this is quite popular. That suppose f is differentiable. F is a function from R to R, and f is differentiable at all points on R. Okay. And suppose f is strictly increasing. Suppose it is strictly increasing. Then can you say that f dash is greater than 0 for all x? Can you? I mean, what do you think? Why it should be, or why it shouldn't be? Or can you give me a counter example why it is? Anyone?
It should be strictly positive.
It should be strictly positive. Okay. So then I will give you this example that fx equal to x2. So is it strictly positive? Sorry, is it strictly increasing? Is this function strictly increasing? Yeah, is it? If a is less than b, then a cube is less than b cube, right?
Yes, it is increasing.
So it's strictly increasing, yeah. And now what about f dash x? It's a differentiable function from R to R. F dash x is 3x squared. And f dash 0 is 0. So if you look at the graph, it is like something like this. Something like that, something like this. It is strictly increasing at 0, but still the derivative is 0. So you can't say. So what you can say is, if the function is increasing or strictly increasing, what you can say is f dash is 0. That is something else. You can't really say about f dash greater than 0 or less than 0. You can't say anything about the strict inequality of f dash, but you can definitely say this. Yeah, so from where are all this coming from? Are they new to the thing called differentiation? Till continuity and limit, we didn't find any counterintuitive facts in calculus. And certainly from when we started differentiating things, we are finding so many counterintuitive facts. No, it's not like that. Let me again go back to this. Let xn be a sequence. Let xn be a sequence of real numbers. And let all the xn's be positive, strictly positive. And also assume that xn converges to L as n goes to L. Can we say that L?
No.
No, right? Example?
1 by n.
Exactly. So this was pretty easy, right? So let xn be 1 by n, this is the sequence of 1 by n. Then this goes to 0 as n goes to infinity, but all the elements should be positive. So this is basically the place from where it is coming. But again, when you change the inequality from this to this, the weaker one, then it is true, right? If xn is greater than or equal to 0, then we can say that the limit is also going to be 0. So this is also something to keep in mind. And this is basically the place from where the derivative thing is also coming. Do you see the analogy? I don't know. It's actually basically the same thing happening there. Here we're taking sequences, and then there and then the same, like we can also interpret this as sequences, but yeah. So the thing is, limit of things which are strictly at some point can go to the boundary of it. That is the whole idea. That is true for derivatives, that is true for sequences. And what is special about the weaker inequality? That it includes a boundary. From the weaker inequality, you can't like again the same thing is this. Again, another analogical thing. That is, if you consider this set of real numbers, that is basically this set. It's a closed set. But when you consider this set, it's not closed. Okay. So now let me go into some more concrete problem solving things now. So let's start with a pretty easy one. Can there exist a function from R to R such that fx minus fy is greater than or equal to 1 by, what is this here? 1 for all x. So what you are supposed to do is try the problem, and if you have any significant progress, just, or if you solve the problem, let me know in the chat, or not the chat, just on videos you can say.
I think there shouldn't exist such function.
Yeah, yeah. Okay. And why do you think so?
If we consider g of x equal to 2021 fx, so it leads that mod of gx minus gi greater than equal to 1 for all reals xy.
Yeah, yeah.
And we can use arguments of contradiction by countability.
Yeah, exactly. So is it a pretty common problem? I don't know. Like, it wasn't used to be when I was studying this too. If all are comfortable with the solution, then we can proceed to the next problem. If not, then we can try a little bit. So for those who are done with this, you can try the next one. So for the next one, I need to define some things like subsequence and stuff. But okay, so maybe we'll get into that later. Or maybe let's just do that. Okay. That's various. Yeah, so whoever is finished the first one can try the second one, and after discussing solution of the first one, I will go through some details regarding convergence subsequences and limit points. After that, we'll move on to the discussion. Anybody else got the first one?
Can you please read out the last line of the second question?
Yeah, so it's basically saying that you can rearrange the sequence xn in a particular way. Let's say after rearranging the newly rearranged sequence is yn, then yn to the power 1 by n is a convergent sequence. You can have such a rearrangement of x as a sequence, given that xn has a subsequence which converges to a non-zero limit. Yeah, so let me discuss the first one. Before that, let us go through. So this is my plan. Okay? So we'll go through problems, and while solving a problem, we'll revisit the required notions and the important theorems of that particular area. So a set is countable, not belonging to this set. A is countable if there exists a bijection from n to a, or if a is finite. Okay. And
Papa, are
then
you
we
typing
know.
something? I cannot see the screen.
Yeah, I can't see your screen.
Okay. Yeah, sorry. Let me go share this. Yeah. A is countable if there exists a function from n to a which is a bijection, or if a is finite. The next important thing is R is not countable. And what we call the sets which are not countable, we call them uncountable. R is uncountable. This is the thing what we need here. But let us go through all the other remarks also, which are important here. Countable union of countable is countable. Uncountable set. So I'm writing them in very less vigorous way, just to give the idea. Uncountable set minus a countable set is still uncountable. That is basically that even if you remove countability elements from uncountable set, it remains uncountable. For example, real is uncountable and natural is countable. So if you remove all the natural numbers from the real numbers, then the set which remains is again uncountable. Rationals are countable.
What is the countable union of countable sets? I didn't understand.
That means that suppose you take union of countably many sets, A1 be a set, A2 be a set. It is going on, countable.
Oh, okay.
And all this A1, A2 and everything, all of them are countable. A1 is countable, A2 is countable, A3 is countable. All A are countable. And now you're taking the union of all of them. So you're taking a countable union here. This is a countable union. And you're taking the unions of countable sets. Then the whole thing will be countable. So this includes all the things like finite union of countable sets or countable union of finite sets or whatsoever. Like all the finite things are countable, right? Yeah, so and Q is uncountable. Sorry, Q is countable. So rationals are countable. So R minus rationals, that is irrationals, is uncountable. Again, a set if S is countable, not like that. We should say that S and the power set of S are not equal. So let's forget about all the big terms. So if two sets can be bijected, like if there is a function from a set A to B which is the bijection, then we often call the set A and B to be equivalent, because bijection in some sense give a same cardinality thing between the two sets. Now, cardinality is something which is just defined for the finite sets. Like there are we also define cardinality for different sets, countable sets. Natural has a cardinality. That is a particular way of defining that. That's different. We'll not get into all that. But yeah, for now, what we expect a high school student to know about cardinality is just the cardinality of the finite sets. But yeah, so a set and the power set of it cannot be bijected. Cannot be bijected. So F from S to S bijection doesn't exist. Okay. Now there are things like you can't get a function from an uncountable to a countable, which is 1, 1. It's not possible. This is not possible. Can you prove that? Can you prove this step using any of the other statements? Assume that all these are true and try to prove this.
We can say it like this, that if the function f is 1 1, then there are at least as many elements in the countable set than as in the uncountable set. Like we can say it like this, but that argument works for finite sets, I guess.
Yeah, exactly. So like as many elements and all that things are, yeah, what you're saying is basically correct, but they're not very well defined notions. So it's basically very easy, okay? So just take the range of the set. So we need another thing here, that a subset of a countable set is countable. So just take the range of F. That is subset of a countable set. Right? So it is countable itself. Now, a function where it's 1, 1 and restricted to its range, then the function becomes 1, 1 and on to both, right? A function from its domain to its range is always on, because range is defined in such a way. Is it clear? Like what I'm trying to say is, if
we are basically getting a bijection from that uncountable set to this range of F.
Yeah. Then we are just contradicting the definition of uncountable. When we are getting a bijection between countable and uncountable, why we can't get that? Because if we get a bijection with that set with countable, then the set is countable. But again, it is uncountable because it's not countable, so it's countable. But yeah, so what I'm trying to say here is that a function from A to its range is always on. Now, but okay, so I will like to give a remark here. That is, in several cases, when we deal with things like this, suppose we have a function from A to B, and then we try to restrict the function from A to its range or whatsoever, or we can restrict the domain or change the domain and range in certain manner. And what we often do is we basically denote the function by the same f and write let's restrict it to some a bar or whatever. So here we are restricting the codomain to the range, but that's not basically correct. You can't restrict the function and then again keep the same, because they're different functions. Like what I'm trying to say is, suppose, let me give a live example so it's clear. suppose we are going from z to z. Suppose f is a function from z to z mapping z to z square. And g is a function from z to n mapping z to z square. They two are not the same functions. G is the restriction of f by restricting the codomain to its range.
Is G
But
even a function? I mean, G of 0 does not exist, right?
yeah, so take natural union 0, whatever.
We can
But like take the range.
non-negatives, yeah.
Yeah, take the range, yeah. But technically speaking, they're not equal. Now, we often do that abuse of notation and we get away with it. Yeah, you shouldn't do that. So getting back to the problem here, what we need to, the essential way of contradicting this statement is that there doesn't exist any such function because R is uncountable. And in this case, the range, so let us first restrict the function to its range. So see, I am just giving a small tilde above it just to avoid the abuse of notation. And how do we define the f tilde? We define f tilde x equal to fx for all x. So it seems to be very trivial, but yeah. So just write one line for the sake of cleanliness. And now we have a function which is, okay, so firstly, this function is 1, 1, right? This function is 1, 1. Why it is 1? Anyone? If there is a function for which this is the case, yeah.
If there exists some x1 and x2 such that they are not equal, but fx1 equals fx2, then this mod will become 0. But
yeah, exactly.
This is not greater than equal to 1 by 2021.
Exactly. So the function is 1, 1. And now we have restricted it to its range, so the function is on 2. So this f tilde function is a bijection from R to the range of f. Now, if we can show that the range of f is countable, then we get a contradiction, and so there can't exist any such function. And why it's countable? Because see, we can divide the whole set of real numbers into intervals like this, intervals of 1 by 2021, 2021 length. Can do them, right? We take 0, 2, then we take 1 by 2021, then 2 by 2021, and so on. So this set where we have, which is the range of f, we can't have any 2 points in one such interval, because in that case, the distance between them will be less than 1 by 20. So there can be at most one interval in one such interval, 1 point of the range set in one such interval. So there is at most 1 point here, 1 point here, 1 point here. And how many intervals are there like this? There are countable many intervals, because you can biject naturally with the numbers very easily, right? The intervals are of the form, say, z by 2021, z plus 1. And z is in integers. So again, z is also a countable set. So the number of intervals is countable. And so the now, of course, so you can compose the two functions and you can do it explicitly, or it's sufficient to just write in words that the range of f will also be a countable set, because it can only have 1 point in one such interval. So it's countable, and again, because we proved that f tilde is a bijection from R to the range of f, there can't be any bijection from R to from an uncountable set to countable set. You get a conclusion. So is it clear to everybody?
Yeah.
Great. So let's now move on to, again, a very important part of sequence series, that is subsequences. So again, so suppose xn is a real sequence. Then xnk is a subsequence. Where nk plus 1 is 3. So these are all just new definitions. What do we actually mean by this? Let xn be a sequence like this. Then we take points. So let's say here. So we're jumping around the sequence. By that, we get another sequence. So by any way, if you're getting a sequence in any such manner possible, in any sort of jumping over that sequence, over the main sequence, we get a subsequence. So there are things like even subsequence, that is, if x1, x2, x3 is sequence, then x2, x3, x4, sorry, x2, x4, x6, so on is called the even subsequence. They are two most important subsequence. And x1, x3, x5, this is called the odd subsequence. Now there are theorems stating that, so see, all the theorems I'm stating here, even in the uncountability, countability part, all of them have proofs, and most importantly, there are many beautiful proofs here. R is uncountability is such a wonderful proof. Then S and the power set can't be bijected, that's also a wonderful proof. And all this, any theorem I'm stating here, of course they have the theorems of mathematics. But I'm not going to go through the proofs of them because, yeah, we're really short of time. So there is a theorem which states that if xn is convergent, that implies any subsequence of xn is convergent. And then there is another very important theorem, the Bolzano-Weierstrass theorem, which says that if xn is bounded, then there exists a convergent subsequence. Convergent subsequence. A subsequence is convergent when it's convergent as a sequence, of course. A subsequence is a sequence in its own right. So we can talk about its limit, its convergence, and all. So that's a Bolzano-Weierstrass theorem. Okay. So I think it's better to state this problem, this second one, in a different set of words. Okay. So now, do you know about limit points of a sequence? So L is limit point of the sequence X. Anybody? You know the definition of it? It's a limit.
If like for any e greater than 0, that there exists a n for such that mod of xn minus l is
Exactly.
less than e for all n greater than
Yeah.
equal to that n.
Yeah. Exactly. Yeah. So what does that mean? That if L is here, take any however small neighborhood around L, we'll find always a point of that sequence xn here. So another way to state is what you said is a perfect definition, which is equivalent to what I'm going to say now, is that there exists a subsequence of xn converging well. Do you agree with me? Are they equivalent? Why do you think they're equivalent or not? What? So yeah, so what we can do is basically we can construct a subsequence in a way that it will converge to L. Because starting with L, we take a neighborhood like this, then we take a we get a point of xn of the sequence xn here, then we take an even smaller neighborhood, then we get again a point of xn here, then we take even a smaller neighborhood, then we get a point of xn here, and so on. We can proceed. So we make these points to form a subsequence of xn, right? And that subsequence will converge to L, basically. So that's the intuitive way to look at it. Yeah. And it's not just constrained to sequence. You can talk about limit points of a set, of a subset of real numbers. Let A be a subset of R, then L belongs to R is a limit point of A if there exists a sequence xn in A, like all the points of the sequence are in A, such that xn converges to L. Again, in other words, L is a limit point of the set A. If for any neighborhood around L, we get a point of A inside it. Why I'm basically stating this subsequence and sequence definitions? Because they're often very useful to handle. The definitions are very useful to apply problems. So is it clear? So what I'm defining here is limit point of a subset of R.
Won't we need the terms of the subsequence to be different from that limit point?
Yeah.
Otherwise, we will get a contradiction.
Yeah. We need that. Like there are, we call there are some definitions like activation point and stuff which includes this and doesn't include that. Yeah. But basically, yeah, it's better to avoid that. It's enough. Yeah, so in that neighborhood, you have to find a point except that L from the subset A. You can't just go on saying, okay, I have L. Okay, so any neighborhood around L has L. So you can't just go on saying, okay, L. Like, but yeah, that's a very valid point. And now what is the problem framing basically? So now you don't need to talk about all that rearrangement and stuff. You can just say that So I can erase this part, right? Is it? So now, can you frame it in the terms of set, limit points, and whatever, except all this rearranging and stuff? So tell me if you agree with this construction, like of this variation of the problem. Say A be a countably infinite subset of R. We know that there is a limit point of A which is non-zero. So the question is, or it's telling us to prove that what we need to prove? We can get a sequence from this set A such that this sequence is convergent. And that's not it. This sequence will exhaust for all A, X, and there must be a n such that X n. I think this is a little bit difficult problem to state and solve now. Of course, I want to also solve it. So maybe this is a little bit advanced for now. So what I'm trying to say is, you can get a, like this set A can be transformed into a sequence in a particular order for which the 1 by nth power of that sequence is convergent. Given that the set, the countable infinite set, is having a non-zero. Is it really getting very hard to follow? Please let me know. Like, try to be very honest with me. I think, yeah, it's nothing much from here. So what the basic idea is, so I will suggest you to try this out when you are free or whatever. Yeah.
Couldn't be like every term of x is greater than 0. Otherwise, like 1 by n power may not exist also if it is negative.
1 by n power doesn't exist if it's negative. Yeah, so again, you can arrange it in such a way that for the even powers,
Okay,
it will exist, or like that. Yeah. Yeah, but that's a good point. Maybe it's in given all this difficulty, you can just, for your sake of being comfortable with all, assume that A is a set of non-negatives. Yes. Yeah, you can try to solve it as you need that, but you don't really need that. So basically, the point is that what was our intuitive definition of a limit point? If it is a limit point, then any neighborhood around it, we have a point which is here, right? So now if it's a non-zero limit point, then what we can say is we can get a neighborhood like this of the form 1 by A and A around it, right? This is also something to know. Any non-zero real number we can find a neighborhood around it, which is of the form 1 by A to A. And for 0, we can't do that. It's again objective question that. So, okay, so let us do a bit more interesting and bit easier problem. We'll get back. So just a small thing. Let L be a real number such that there exists a real number so that L is in 1 by A. So the question is, what is the set of all these real numbers satisfying this? This is basically, as I discussed, this is basically R minus 0. So 0 is the only number for which you can't do that, right? Except that for any number, you can find A, so that 1 by A, in between A and 1 by A, there is that. So just keep that in mind. I just gave out one possible object question of this one. Yeah, so where were we? Yeah. So for this, in this case, because L is non-zero, we can get such an interval, and then we can start considering points inside it in such a way that you can take these powers to these, like you can take a power 1 by a power n and a n, and then take sequence of intervals and then points in all those intervals, which again makes a sequence, and try to then power it by 1 by n. They will converge or something will happen. So yeah, so try to figure this out. Think about it, give it some time. I don't want to rush this problem. I think that will be difficult to understand. So yeah, think about it. But yeah, for this problem, we covered the basic notions of subsequences and the theorems related to it and the limit points. So that's what I wanted to do. Now, yeah, so is it clear, like anything, any remarks or any doubts or anything about the subsequences, Boltzmann Weierstrass and things like that? If not, then let us do another interesting problem. Let f and g be two functions closed AB2, open 0 infinity. They are continuous both, such that g of x naught is less than f of x for all x. Now, you need to prove that. Sorry. Yes. So you need to prove that there exists lambda greater than 1, such that f is greater than or equal to lambda g in A. It's very easy.
Can we consider the function h of x as fx minus gx? So h of x will be a continuous function in a closed interval, so it should attain a maximum value, and like after that we can just define lambda so that if such that fx is greater than equal to lambda g, like that.
Yeah. So what we're saying that h, we define h as f minus g. Then
Yeah.
then
So
h is greater than 0 for all x in a b.
And
Then
h will be a continuous function in a closed interval, so it must attain a
Yeah.
maximum value.
Yeah. So
So after that, we can like suitably define lambda so that f is always greater than equal to lambda of g. Because I mean,
even
we are
if that
just
is the case,
taking the greatest value between greatest value of f minus g. After that, we can just define lambda like that, I guess.
no, wait. So even if h is greater than equal to lambda, then we are getting that f minus g is greater than equal to lambda. What we need is f is greater than equal to lambda g. So some sort of f divided by g is going to be something like that. So how from this difference function you are going to end up here, where we're kind of considering the ratio of the two functions?
Okay, let me think for a while.
Yeah.
Oh, instead of considering the function f minus g, I think it will be helpful to consider the function f by g.
Yeah. So how will you do that? Like, yeah.
I think it's just still an idea. So we define h of x to be f by g, and we know that h is continuous because
Just a sec. So h you are defining as f by g. Yeah.
f by g. Now we know that the range of or the codomain of both f and g is the positive reals. So this is always defined.
Well defined. Yeah.
This is always well defined, and this is also continuous. So it should attain a minimum value in that interval somewhere.
This should again a minimum value, that interval somewhere.
Yeah. So
Definitely.
there exists a lambda so that h is always h of x is greater than equal to lambda for all x in a and a comma b.
Yeah.
And uh, this lambda will obviously be greater than 1, and I guess we are done then. Because I mean, we are given that f by g is greater than 1 always. So their minimum value will will obviously be
But
greater
it
than
can
1,
be
right?
1, right? It can be 1. How do you know that it's not 1?
We are given that f is strictly greater than g. So
Yeah, fine. So now you have a function h for which h is strictly greater than 1 in the interval AB, right? Now, but again, coming back to the first thing we discussed today, there can be a function which is strictly greater than 1, but the minimum is no, but yeah, so, yeah, but again, the minimum must attain. So, is it so easy? I don't think it's so easy. H is greater than 1, fine, there is a problem here. Then we are getting, so it's the function on the closed interval AB, which is strictly greater than 1. Now H is a function from, yeah, yeah.
I think that problem that you're talking about with the function with being always greater than 1 but somewhere being equal to 1, I think that problem will arise if we take the limit or something, because then the inequality weakens. But here we are given that h is strictly greater than 1. So will a problem arise in this case? I'm not sure.
I understand. Yeah, I think this works. But if this works, then what my solution was is very stupid. Just let me think it again. And of course, everybody else also keep on thinking and trying to find some mistake in the solution. Like, of course, I'm not saying the wrong way, but yeah. Okay. So yeah, I think it's correct. It's correct.
I thought of this in the same way. Not getting any flow.
Okay. So it's correct, right? Can we find anything wrong with it? I don't think so. Yeah, it's fine. All the steps are clear.
Can you share your solution also? Maybe the things that you use in your solution will help. Like,
Yeah, I was thinking to apply some variables and analysis here. Like, so yeah, so let me go through my solution. But I think what I was basically doing is proving that some stupid thing. Yeah, I was basically trying to prove. I was kind of doing the proof that a function attends is minimum, like close to some kind of some proof like that. So my solution was like this: that what is a let's assume the contradiction. Okay? So what does that say? If this is not true, then what is the case that for any lambda strictly greater than 1, there will be some point for which f will not be greater than equal to lambda times g in f, right? So that is basically this, that for any small epsilon, there exists a point for which f is less than equal to, like there is some point x such that fx is less than equal to 1 plus epsilon g, or strictly less. So this is the converse, right? Like if this is not true, then this should be true. That for all epsilon, there exists x in AB such that fx is strictly less than 1 plus epsilon x. So instead of this epsilon, you can go on finding if xn, which is strictly less than 1 plus 1 by n of gx. Like what I'm doing is I'm basically taking 1 by n. Now 1 plus 1 by n is strictly greater than 1. And we are assuming that this is not true. So there must be some point for which this is true. And we are calling that point xn. So by that way, we're getting a sequence xn for which this is true. Now xn is a sequence in this closed and bounded interval AB. So xn converges to, like xn has a subsequence which converges to some limit point. So let's say that limit point be x0, like x0. And then what happens is you take the limit of that. Then when you're taking the limit of both sides, and this goes to 1, this goes to f of x naught, and the inequality remains like this. This strictly less than becomes less than equal to, and g of xn becomes 1, like it's 1 times g of x naught. So what we get is f of x naught is less than equal to g of x naught, which is not possible because this is given. Sorry, so, some the inequality got reversed. Yeah, I don't know what is it. Yeah. This contradicts this. I'm writing f here, g here, and then it will reverse. Sorry for that. Yeah. So is it clear what I was trying to do? I think the techniques will be helpful. Your solution is quite smart in this case. Yeah, very short. What I did basically is construct a sequence for which this inequality is not holding, and then from that sequence find a point in this interval where this is not holding. That is what I basically did. Yeah. So now tell me this, that what if we replace this closed interval by open interval? Will it be true? Will it be still true? If not, then you should give me a count. But one thing I can say here, that is, if we don't give this information to you, I just give this to be R, then your method will not work, but mine will still work.
Right, and
Do you see my point?
if the domain was also given to be an open interval, then also I would not have that theorem that
Yeah, but if the domain is given to open interval, then I also don't have Bolzano-Lewis.
yeah, right.
Yeah, but the thing is, for open interval, the statement is not true itself. So you can find a counter itself. Try to like construct a counter itself. And please let me know if there are some doubts or anything. Like, I'm not sure if I'm going fast or whatever, if my handwriting is clear. So feel free to comment on anything you want to change or something I need to modify, whatever. So I basically chose this problem because the solution I had included all the concepts we were dealing with today. So you have this equality, like strict inequality transforming into weaker inequality while taking limit. Then we have Bolzano-Lewis theorem. So I thought this might be, yeah, but still it's a good problem. And now when you are changing when you are not giving us closed intervals, then it will make a problem. You know? For example, counter example, you can take this. I will remove this upper part. Then take this. F to be, say, x, fx to be x, and say g of x to be x. And what should be the interval AB? Any guesses?
0 to 1.
Yeah. So see here, x square is less than x in 0, 1. That's true. But you see that you can't find any strict lambda greater than 1 for which x square is less than equal to, like, this is true in 0. Because, cancelling both sides, you will get x is greater than lambda. This essentially means that x is greater than equal to lambda for some lambda strictly greater than 0. And x can be anything between 0. So this is not true, of course. So this same statement won't be true in the case of open intervals. So this is another generic remark I want to make here. I don't know if making all these remarks are useful now, but at least when I retrospect in my learning in 10+2, I think all these remarks would have been useful. The thing is, there is something called compact sets. I don't expect any of you to know what they are. These are something which occurs like many times in topology, or even when you are doing other parts of analysis, a little bit. And wherever is complex analysis, like the whole analysis, compact sets plays a very important role. Now, on R, the compact sets are just closed interval sets. They are the compact sets. These closed intervals, they are really special. Like, not just the closed intervals, the closed sets, like closed and bounded sets. If a set is both bounded and closed, then we can do a lot of things. The Bolzano-Versus theorem, and then there is something called uniform continuity. Your function is continuous on a closed and boundary interval, it's uniformly continuous. And there are many different theorems coming from the same basic understanding of closed and bounded. All the good things happening here and not happening in the open sets is basically the same thing manifesting into many different aspects of real analysis. So these are the very, very general notions you should be caring about. Okay, so let's.
Can you give the definition for compact sets? I actually don't know what they are.
Yeah, so the definition of a compact set is in a topological space, a compact set is a set for which any open cover has a finite subcover. I know nothing of this will make sense, but yeah, you don't really need to know that. What is very fortunate is in case of Rn, a subset of Rn is compact. This is again a big theorem of topology. Compact if and only if A is closed and bounded. So inside Euclidean spaces, we don't need to worry about compactness in general. Closed and bounded is sufficient. And there are again good theorems. A continuous function, if it is continuous, it maps a closed and bounded interval to again a closed and bounded interval, right? This is what happens in general with complex sets. Functions map complex sets to complex sets. So while working in Euclidean spaces, you don't need to really worry about in general compactness because it's sufficient to check closed and boundedness. Now, I am not sure if you guys know what we really mean about closed sets. Closed sets are not really the closed intervals. Like they are closed sets, but in general, this is also a closed set. 1, 2, 3, this is a set in R. This is a closed set. Whereas this in R is not a closed set. It's not closed, it's closed. So again, actually we are quite equipped because we could have studied limit points to define what a closed set in R is. A closed set in R, a subset of, so let me just define it quickly here. These are not very much relevant for ISI syllabus, right? So A in R is closed if this happens. What happens? If L is a limit point of A, then L is like all the limit points are inside the set. If that is the case, then the set is closed. See here, this is not the case. 0 is a limit point of this set, but 0 is not inside the set. So it's not closed. Closed intervals are closed. Open intervals are not closed because A and B both are limit. A is not a member of the set, but still A is a limit point of the set. Any neighborhood around A will have some point of this interval, right? You can't take any neighborhood around A which is free of the whole set. So see, A and B, they're the boundary points. They're the points, like the points exactly are not in the set, but still they're the limit points of the set. So that is the reason this is not a closed set. A set is closed if all the limit points of it are inside the set itself. And bounded, you know the definition of bounded, of course, is bounded by something. So if a set is closed and bounded, then all these beautiful things are true. That a continuous function maps a closed and bounded set to a closed and bounded set. In other words, if a continuous function is defined on a closed and bounded set, it will achieve a maximum and a minimum. All these things. So actually, this was a good thing to discuss because we discussed all those theorems regarding compactness, and all of them are very important. Okay, so let us end with doing another problem, I guess. And please, If you have any doubt, any remark on whatever, if you want to understand something more, if you aren't clear with the solutions I discussed before, let me know. Before the end of the class, let me know. Okay. So let us do a nice problem. From a closed interval 0, 1 to closed interval 0, 1, x is a function which is continuous such that f of x is equal to x. F of x is equal to x. Sorry, is equal to f. Now we define a set as EF, which is defined as all the points in the closed interval 0, 1 such that fx is equal to x. So first prove that EF is non-empty. This is called the Brouwer fixed point theorem. So you can just prove it and then try to prove that EF is an interval. So, okay, we'll discuss what is an interval. First question is that. And the third is find all functions, all such functions, all such functions, all such. So firstly, what is an interval? What is the meaning of this word? Anyone? So, guessing definitions in mathematics is a very good way. It's a very good, like, you can be assured if you can define things well that you have understood the subject well.
I don't know if I'm wrong. I think it means that all the numbers will lie from some fixed number A to E.
What do you mean by lie from? Like
lie between.
Lie between. So is this an interval? Like again, between and from, there are inequalities and strict and open, and there is stuff like that. Yeah. So you can do a very, so you are right. Actually, you are right. But what I'm saying is, you can of course try to brute force the thing down. You can say that okay, anything like this is an interval. Anything like this is also an interval. Anything like this is also an interval. Anything like this is also an interval. And we know that there are only 4 types of things in all the texts of whatever the CBSE and ISI books or West Bengal book books. Will have all these 4 kinds of intervals, half open and whatever they call it. So these are the 4 types of intervals on R, and you can vary A, B in R, and whatever we get, all of them are intervals. And these are the intervals. That's essentially correct, but can we formulate the concept of interval in a more meaningful way than just writing the cases down? So check if I am correct. An interval is something, a subset of R is an interval if this happens. What happens? We say it is called interval if A less than B is in A, then AB, like all the points between A and B, is a subset. This is what we basically want from an interval. To call a set an interval, we want this sort of thing. That is, now you can go over all these 4 types of interval. Doesn't matter in which kind of interval you are working in. But if there is an interval and you have 2 points inside it, then you have all the other points also in between. There is no kind of gap in between. That's what we always thought about interval also, consciously or subconsciously. The idea of interval in our head is exactly the same. That whenever there are 2 points, there is no gap in between. All the points in between are also in that interval. So
In
this
this
is
definition, aren't we defining interval using an interval? I mean, the
are
definition
we?
uses the
Are
that
we?
a comma b.
This is a set. No, this is defined as a set X in R, such that X is greater than equal. This is the set. This is not the only interval, right? This is just a set. This is defined like this.
Okay, we are first defining that closed bounded interval and
Yeah,
then
yeah, yeah.
using that to
Yeah, of
define
course.
others.
Of course, of course, of course. This is a notation. This is not even a definition. This is a notation of like the way we denote set. This is the way we denote set, right? This is a set containing ABC 3 elements. So without writing all the elements between A to B down, we just denote that set like this. It's not really anything new. And now when you are talking about intervals, we can just define intervals to be all the sets of this form. Sorry, all the sets of this form. That is also true. We can define interval like that. Because now you have to prove it, but you can prove it, that any set satisfying this property in R is one of the four. Is it one of the four form? But so in R, they are all equivalent. But when you are going to higher sets, there might be some other sets also where you can do the similar stuff. There are all these things. There won't be some intervals like this. There might be. This is a general way to define intervals. Okay, so we won't get into all that. Let's delete this and let's focus on the problem. So try to solve this. I'll be back. Yeah, so any progress or any solution?
Can you please wait 1 minute? I'm trying the first part.
Yeah, yeah. And I think we don't really need this thing for the first part. For the next part, we obviously need that.
Can I try once? Like, I'm not very sure.
Yeah. Sure. Go ahead.
Suppose there exists some point such that fx is greater than x somewhere, and then it is less than x somewhere.
Okay.
Then by continuity, there will exist one point such that fx
Yeah.
equals to x.
Yeah, but how do you say that? Like it's true, but just one more line on it.
Yeah.
How to say that?
So I assume that fx is greater than x or fx is less than x for all x.
No, I'm saying that suppose fx is greater than x for some x and fx is less than x for some x, then how exactly do you say?
Function fx minus x.
Exactly. Yeah.
Then
Yeah. Great. Yeah. Exactly. Yeah. Now you can proceed. Yeah.
So suppose fx greater than x for all x, then
Yeah.
I take some x1. Now suppose f of x1 is equal to y,
Okay.
then f of y is equals to again f of x1.
Right.
So which is again y, but I had assumed that f of y will be
exactly
greater than y.
Right. Very good. Yeah. But so what I was saying is, do we really need that? Because you see, f of 0 minus 0, this is always greater than 0, right? Because if it is 0, then we are done. Then f of 0 equal to 0, so this is not equal to 5. If f of 0 is equal to 0, then 0 is inside this set of fixed points. But that is not the case we are assuming. So f of 0 minus 0 is equal to 0. Now, f of 1 minus 1 is strictly less than 0. If one is not inside. If 1 is inside it, then it's non-empty. So if assuming that 1 is like it's empty, then f of 1 should be here, right? F of 1 should be inside 0, 1. F of 1 can't be 1. So f of 1 should be inside 0 to open interval 1. So it should be essentially less than 1. So f of 1 minus 1 should be less than 0. Right? Now, so if this is g of 0 and g of 1, like we construct g of x to be f of x minus x, then g of 0 and g of 1 are having different signs. So they must have a fixed point. Like g must have a root sum. G must have a 0 sum. So some g of c is equal to 0. So g of c is equal to 0. F of c minus c is equal to 0. So f of c is equal to c. Right? So we never really use this. Anyway, so now using that is also another way, which is also fine. See, I'm erasing this. That is not a problem, right? If there is a problem to anybody, then let me know, then I will write the solution. That is not an issue. But I don't really want you to copy the solution into whatever. I want you to understand what the solution is about, what the problem is about. So the first part is done, right? And it's done without even using the most important condition of the problem. So now about the second part. What can you say about the second part? EF is actually a closed interval, more specifically. So what I claim is, firstly, yes. So what I claim is firstly this range of f, the subset of f. Why is this true? Suppose f of x is equal to y, then f of y is equal to what? Is equal to f of x, which is again equal to f of x is equal to y. Right? See, f of x is equal to f of x from here. F of x is equal to y is from this. So f of y is equal to y. So for any y in the range, we have f of y is equal to y. Right? So any point in the range is also a point in EF instead of fixed points. So this is true. Now we also want to prove the converse. That E of f is also subset of the range. How do you prove that? So let x be in E of f. That implies f of x. Now take it's clear, right? If f of x is equal to x, then x is being mapped to x. So x is in the range. It is clear, right? There can't be any confusion there. There shouldn't be any confusion.
Can you shift to the
if
previous
x is,
page once?
yeah, sure.
Yeah, okay, thanks.
Can you please explain once why range of f will be a subset of EF?
Definitely, yeah. So see, if y is in range of f, then there is a x such that f of x equal to y. If y is in range of f, then there exists a x such that f of x equal to y. Now, if that is the case, we compose f again on this equation. So f of y is equal to f of x. Y is equal to fx. So f of y is equal to f of x. Now f of x is equal to fx because of this equation. Again, fx equal to y because we assume that. So f of y is equal to y.
Okay, got it.
So the range of the f is a subset of EF. Again, the EF is subset of range. That is also very clear. If x is in EF, that means f of x equal to x by definition of the set EF. And then, of course, if f of x equal to x, then the x point itself is mapping to x. So x is in range. Right? So what we say is, what we finally write is EF is equal to x. Now, f is a continuous function. F is working on AB closed interval. So its range must be this. This must be the range. Right? The range of f is also closed and bounded interval in R. Why is that so? Why is the image of a continuous function on a closed and bounded on a closed interval is again a closed? Why is that so?
We know that a continuous function in a closed bounded interval attains a maximum and a minimum. And
Yeah,
then
so
we
let the
can
maximum
use
be
the,
n, let the minimum be n.
yeah, and then we can use the intermediate value theorem to show
Exactly,
that all
exactly.
of the
Now we can,
values are attained.
yeah, definitely. So now intermediate value theorem, so all the values between m and n are attained. So it's just the same. It's doing a weird notation combo here. So that is just this was just an application of what could be. And now try to figure out the third one. Okay, so the third one is we can't extend it any further. So basically, the functions satisfying this is equivalent to the functions having this. Okay. And we can't say any further about such functions. This is all we can say. What we can say about them? That fx equal to x, set of all points like this, is just same as the range of the function. So intuitively, what we are saying is some points are being mapped to itself, and the other points are being mapped to these points. They're not mapped to anything else. They're somehow mapped to this points. And of another thing I think we can say, or yeah, like they are the same thing. They will imply this. This is the most we can say. I just added the part to make the question a little bit heavier. But yeah, I don't think there is some particular answer of function satisfying this. Because trivially, there can be so many functions like this. No any, like at least I can't see any other way to smaller or bigger functions.
If it's a polynomial, then we can say that like f is either constant function or fx is equal to x, no?
If x is a polynomial, then yeah, I definitely think so, because there is firstly there is a degree argument, very firstly, which is appearing to be.
Yeah.
And yeah, definitely. I think so, yeah. Yeah, if it's a polynomial, then it's either x or it's a constant. Yeah, that's correct. Okay, so we can call it a day. And yeah, so let me know if there is any doubt. Okay? So today what we did is we basically went through, I don't even remember what we started with. Yeah, we basically went through decreasing, non-decreasing, increasing, and their relation to derivatives. Then we talked about sequences, subsequences, and limit points. And then we spent some time on countability and uncountability. And yeah, then we solved some problems and also discussed about complex sets and their behavior and how they're important for theorems and problems. Yeah, these are the things basically we did today. And I think there will be another class on calculus. So there we will be mostly focusing on MBT theorems for derivatives and as well as for integrals. Because the MBT theorems are the next part of the calculus course or whatever you call it, which is the calculus syllabus, which is the most important part. Like that itself covers a weightage of around 50% of the whole calculus thing. Like, of course, I'm talking about questions. Conceptually, everything is as important. Okay, so that's it for today. If there is no further doubts or anything, you can end the class.